In this video, we're going to talk about the Noble Gas Shorthand for electron configurations and its relationship to valence electrons and ion electron configurations. So just as a reminder, in the last video, we learned how to write full electron configurations using the periodic table. Right, so this periodic table doesn't have my different orbital blocks marked on it, but those can easily be drawn in. Those first two columns and helium represent the S block. The transition metals from 3 through 12 for the column numbers represents your D block. The P block is over on the right-hand side, columns 13 through 18. So I'm just going to write my sub-level blocks over each one. And then, of course, at the bottom, we have, in the lanthanide-actinide series, my F block. And if I want to write the full electron configuration for sodium, for example, I just need to know where sodium is on the periodic table. And then I start with that first row in the upper left-hand corner, and I just write down each principal energy level, represented by the row number, and sub-level that I have to go through until I reach sodium. So at that first row, I have to go through 1s2. And then that brings me, once I go all the way through that first row, I go to the second row, and that brings me to 2s2. I have to go all the way across the row, so that also gives me 2p6. And then I start on the third row, and sodium's that first element, so that's 3s1. And that's the full electron configuration for sodium. I'll bring it up just a little bit more neatly here. Okay, now what the Noble Gas Shorthand does is it separates this full electron configuration into two parts. You have the last row that was actually filled, where sodium's located. So that's the 3s row, and sodium was the first element, so it's just 3s1. These are what are known as valence electrons, and valence electrons are those that occupy the outermost energy level of an atom. In this case, for sodium, that outermost energy level is the third principal energy level. And this is separated out in the Noble Gas Shorthand from what we call the core electrons. So these core electrons are those that occupy the inner energy levels of the atom. So in this case, the electrons that we were covering in the first and second rows, or the first and second principal energy levels. Now, in terms of the electron configurations with the letters and the numbers, it's not always easy to visualize this as outer and inner electrons for a particular atom. So sometimes I like to bring up that old picture of the atom, the Bohr model, where we represent our electrons as basically orbiting around in rings the nucleus of the atom. And when you do that and you recognize that each of these rings is supposed to represent a principal energy level. So for sodium, it's got 2 electrons in that first ring. And then when we move to the second row, it represents the second energy level, so we're a little bit farther out. And we've got 8 total electrons, 2 in the S and 6 in the P, in that second energy level. And then finally, we've got our last electron, that 3s1, in that third energy level. Now, it's nice to be able to visualize that with the Bohr model of the atom, because it makes it very clear that that S1 electron is the one that's outermost. And we are actually most interested in those valence electrons, because the electrons on the outside of the atom are the ones that are going to interact with other atoms. And these are the electrons that are going to be involved in chemical bonding. And when it comes to looking at atoms, really, that's one of the most important pieces that we're interested in. How do these different atoms interact with others? And it's always the valence electrons that are going to be the ones interacting, the ones on the outside. The core electrons don't do much. And so what the Noble Gas Shorthand does is essentially it just condenses that core, which is usually the largest part of your electron configuration, into the noble gas that it represents. Because it turns out those inner rings will represent the noble gas of that element from the row above. in the case of sodium, that 1s2, 2s2, and 2p6, well, that's the exact same electron configuration as neon. So that's the noble gas from the row above. What this then, our noble gas shorthand for this electron configuration for sodium would be neon. We put the symbol for neon in brackets saying the core of this particular electron configuration is neon. And then on the outside, we've got our valence electrons in that outer ring represented by one electron in the 3s orbital. And this is your noble gas shorthand for your electron configurations. Okay, so let's do another noble gas shorthand. So this time we're going to do the shorthand electron configuration for sulfur, which is located right here in the p block. Now, I've got my periodic table outlined with my different orbital blocks. So this is S, this is D again, this is P, and this is F. And the big difference here for doing the noble gas shorthand is that I don't have to start all the way up in the upper left-hand corner of the periodic table this time. This time, we are going to just go to the row above the element that we're interested in. And we're going to go to whatever the noble gas is in that row. So whatever's in column 18, we're going to say, basically, I could have started at the beginning, but everything that I would have done, would have filled in, would be exactly the same as the electron configuration for that noble gas, for neon. So we're just going to go ahead and take the element symbol for neon and put it in brackets. And then we just start straight from neon, we go straight to that row that actually contains sulfur. And we go across it and fill in everything above neon. So we start at 3s, and we have to go through both of those columns. So that's 3s2. We continue with the third row over in the 3p block. That's where it picks up again. And sulfur is the fourth element in that p block. So that is 3p4. And that's my noble gas shorthand for sulfur. All right, so that's a lot simpler, right? We don't have to start all the way at the beginning. We can actually just go to the noble gas in the row above whatever element we're interested in and write the electron configuration from that point forward. Now, in terms of valence electrons, right? Remember that valence electrons are those occupying the outermost energy level of that atom. Well, that's, in this case, is the third energy level. And I have more than one valence electron this time. For sulfur, I have valence electrons both in that S and that P sublevel. So my valence electrons, that's actually 2 plus 4, or 6. Okay, so it's that combination of whatever's in the S and in the P. Okay, let's try another one. This time we're going to do calcium. So calcium is in the fourth row. And it's atomic number 20. Now again, we're not going to start all the way at the beginning. We're just going to go to the row above it, which is the third row, and the noble gas at the end of the row above calcium. So in this case, my noble gas that I'm starting with is argon. That represents my core. Everything that came before row 4, argon contains. So we just have to write the symbol for argon, and then we go and start with that fourth row. So calcium is in the 4s block, oops, and it's the second column, so it's 4s2. And that's the noble gas shorthand for calcium. And in terms of valence electrons, this is my outermost energy level. It's the fourth principal energy level, and I have 2 valence electrons in there, so that is my total. I have 2 valence electrons, so I'm just going to abbreviate that as VE at this point. All right, let's try one more. So our last one is going to be gallium. So gallium's atomic number 31. So it's also in the 4th row, but it's a little farther over. All right, so again, we're just going to go to the row above it and all the way over to the noble gas at the end of the row above. And so it's going to have a core that's going to be the same as argon again. And then we start in the row that contains gallium and write everything that we go through, all of the different sublevels until we reach gallium itself. So we're going to start with 4s, 2, and then we move into the D block. And this you have to remember that the D block is actually from the energy level below. So that big number in front is going to be 1 less than whatever the row number is. So this is actually 3D. We go all the way through that 3D block, so that's 10 spaces, until we hit gallium, which is at the beginning of the P block. And the P block is back on level with the row number, so it's part of the 4th energy level again, and that's 4p1. Now this is an interesting electron configuration, and we start seeing this more and more for our bigger atoms. You start seeing these D sublevels that technically are not part of your outermost energy level, right? My outermost energy level technically is really my 4 S and P, right? That's the 4th energy level. And so when you're trying to count valence electrons for these types of atoms, you really are picking only those valence electrons that are in the S and P at that highest energy level. So for this one, we would actually say for valence electrons, we have 2 from the S plus 1 from the P, which equals 3 valence electrons total. But what do we say about those 3D 10 electrons? Well, those are called pseudo-core electrons, right? They're not actually part of the noble gas. Argon does not have any electrons in the 3D sublevel. So we can't put them in there with the noble gas, but they're also not part of that outermost energy level. Now, they're called pseudo-core because, quite honestly, they can take part in chemical reactions. They can interact with other atoms. However, it's always those valence electrons, the ones from the outermost highest energy level, the S and P, that will react first. So just as we know that there's a pattern between the last sublevel being filled for an element and its column on the periodic table, there's also a pattern for the number of valence electrons that particular element has. So for example, we know that every element in column 1 is going to end its electron configuration with S1. Well, that means that it has, for its valence shell, its outermost ring, it only has that 1 electron in that S sublevel. So every single element in column 1 of the periodic table contains 1 valence electron. In column 2, we end with S2. And no electrons in the P sublevel at all. So that means that every single element in column 2 actually contains 2 valence electrons. And we're going to ignore those transition metals for a second and move down to the first column in the P block, which is column 13. So column 13, in that outer level at that final row, will have, every single one of them will have 2 in the S, from the beginning of the row, and then 1 in that P sublevel. Well, for valence electrons, we add both the S's and the P's, so that becomes 2 plus 1, which gives you 3 valence electrons for everything in column 13. For column 14, it's S2P2 for that highest energy level. Well, the total of that is 4 valence electrons for everything in column 14. And we keep going down, right? We keep adding one more to that P sublevel as we go across the periodic table to a new column. So column 15 has 2 in the S and 3 in the P, so that gives us 5 valence electrons for everything in column 15. Column 16 is 2 in the S and 4 in the P, so that's 6 valence electrons total. 17, we have 5 electrons in the P sublevel. Combine that with the 2 in the S at the beginning of the row, and you have 7 valence electrons total. And finally, for everything except helium in column 18, you have a completely full P sublevel plus the S completely full sublevel, and so you have 8 valence electrons total. And there's even a pattern here between the column number and the number of valence electrons, right? There's one, column 1 has 1 valence electron, column 2 has 2, column 13 has 3, so it's that last digit there, 14 has 4, 15 has 5, and so forth. 16 is 6, 17 is 7, and 18 is 8. All right, so we can just look at the periodic table, and we don't even have to think about its electron configuration or its noble gas shorthand. We can just look at that column number and predict the number of valence electrons, at least for those representative elements, those that fall in those S and P blocks. The transition metals, though, the ones in columns 3 through 12, are a little bit trickier. So you already know that these are the metals that will actually form multiple charges, right? Iron can be +2 or +3. These are the ones that are just a little hard to predict anyway. Well, part of the reason they're hard to predict is because they're the ones with the final electrons going into the D sublevels. And as we explained in the last slide, those D sublevels can, in some cases, participate in chemical reactions. And what that means is that they can contribute to the number of valence electrons. It just can be a little bit harder to predict for those transition metals. It depends upon the environment that metal is actually found in. So it's harder to say consistently that they're always going to have 2 valence electrons or 3 or 4. It's going to depend upon the environment it's actually in. Now there's another pattern that you've been introduced to relative to columns and the properties of the elements within, and that's your ion charge. So you already know that for those representative elements, in column 1, all of those metals, when they form ions, they chemically react to lose electrons. They consistently lose 1 electron and form a +1 charge. In column 2, all of those elements will form ions with a +2 charge. And the metals in column 3 will be +3. We also see some consistent patterns with our non-metals on the right-hand side of the periodic table. Those in column 15 or 5A tend to gain 3 electrons to get a -3 charge. 16 or 6A get a -2 charge, and all those in column 17 or 7A get a -1 charge. So ion formation is all about electrons, either being lost or gained. And so this particular pattern also relates to those electron configurations, this time for the ions. So let's start looking at some of these ion configurations. And we'll start with sodium. Sodium is in the 3rd row. It's in column 1, so we know that that means it has 1 valence electron, and that valence electron is in the 3rd energy level, so 3s1. We also know that all those metals in the first column will, when they chemically react, tend to lose 1 electron to become an ion with a +1 charge. Well, the electron that they're going to lose is going to be the one that's on the outside of the atom, and that's the valence electron. So if a neutral atom of sodium loses that 3s1, what's left behind for the ion is going to be the core electrons that basically have the same electron configuration as the noble gas neon. So the ion electron configuration for sodium is actually just whatever the electron configuration is for neon, for its core. We're going to see a similar pattern for magnesium as well. Magnesium in column 2 has the 2 valence electrons, And those metals in column 2 tend to lose 2 electrons to become a +2 charge. Well, they're going to lose those valence electrons. And again, when they lose the 3s2, what's left behind is just the noble gas core. So the magnesium ions have an electron configuration that is similar to that of neon, of the noble gas neon. And we see the same pattern for aluminum. Aluminum forms a +3 charge when it forms an ion. Well, it only has those 3 valence electrons. So those are the 3 electrons it loses. And again, we get that noble gas core, that neon configuration for the ion of aluminum. And this is a consistent pattern that we see for a lot of our stable, consistent ions that form a consistent charge, so that they tend to lose electrons to reduce themselves back to that noble gas core. Now we see something somewhat similar for our nonmetals. So nonmetals like oxygen and fluorine, instead of losing electrons, they're going to gain electrons. So they become anions with a negative charge. And to some extent this makes sense because it's going to be pretty hard to lose a total of 6 electrons. It's much easier for an oxygen atom to just gain 2 electrons. When it gains those 2 electrons actually go into that p sublevel. That's where we would continue adding electrons, since that's where it's not completely full yet. So those 2 electrons add on to that 4, and what they do, they actually give us, instead of helium 2s2 2p4 in the ion form, we actually end up with helium 2s2 2p6. Okay, so that's the electron configuration for oxygen with a -2 charge, and that's the exact same as neon. That's a noble gas configuration as well. It's not the noble gas core for oxygen. The core was helium, but it now has that electron configuration of the element at the end of its row. And fluorine does the same thing. So fluorine in column 17 or 7a, these all tend to gain 1 electron to get a -1 charge. Well, that electron is going to be added into your P total. So we're going to end up with, again, a helium with a 2s2, so helium at the core, and then 2s2 2p6 for the ion electron configuration for the valence electrons once we've added in that extra electron to get the negative charge, and that's the same as neon. And we consistently see this pattern that our ions, our atoms tend to gain or lose electrons to obtain the electron configuration of a noble gas. And that's because there is a certain stability associated with that noble gas electron configuration. And we know that noble gases are called that because they don't necessarily react. And the reason they don't react is because they don't have to. They actually already have a full S and P sublevel. Atoms tend to react, they tend to lose electrons or gain electrons, or, as we'll see in the next unit, they tend to share electrons so that they can gain a full set of S and P electrons, a full set of valence electrons for its outermost energy level. Now I want to clarify one thing. When I say that the ion electron configuration here is the same as neon, for each of these ions, I'm not saying that sodium has magically transformed itself into neon or magnesium has done so. I am just saying that it has the same electron configuration. That means it's isoelectronic. That's another term you might hear, having the same electron configuration. At the nucleus, sodium is still sodium. It still has 11 protons. We haven't altered that component of its identity at all. We've simply changed its chemical reactivity by changing the number of electrons it has orbiting that nucleus. Now, those were all examples of representative ions, those that come from elements in the representative columns, the S and P blocks. But what about those transition metal ions? So you know that the transition metals and our heavy metals often can have multiple charges. These are the ones that we have to specify with the Roman numeral. So iron is a great example. Iron is located on the periodic table. It's element number 26, which is right there in the middle of the D block. And its electron configuration with the noble gas shorthand is actually argon, is the noble gas from the row above it. And then in the fourth row, we go through 4s2, and then it's the sixth element in the D block, so it's 4s2, 3d6. Now, when iron forms an ion, it's a metal, so it tends to lose electrons, but it's not consistent necessarily in how many electrons. There are two common ions that can form from iron. You can have iron with a +2 charge or iron with a +3 charge. So iron with a +2 obviously has to lose 2 of its electrons. But which of these electrons does it lose? Well, it's always, when you start losing electrons, you're always going to lose from those S and P sublevels first. So when iron with a +2 forms, the 2 valence electrons that it loses are the ones in the S sublevel at that highest energy level, at that 4th energy level. So the electron configuration for iron with a +2 charge is just argon 3d6, nothing in that 4s sublevel. Now, iron with a +3 charge has to lose 1 extra electron. So it turns out that the extra electron then, that third one, will actually come from the 3d sublevel. So a lot of the patterns that we see with the transition metal ions, we get those multiple charges because the transition metals start losing additional electrons from those 3d or 4d or whatever energy level the D level is from. They start losing electrons from those D sublevels in addition to the valence electrons. But as a general rule of thumb, electrons are always lost from the valence S and P sublevels first, then the pseudocore D sublevels. In summary, valence electrons are the electrons from the S and P sublevels at the highest energy level of an atom. These are the electrons that are on the outside of the atom and can participate in the formation of chemical bonds. When ions form, electrons are lost or gained from the outer or valence portions of the electron configuration to form an electron configuration that is more stable, like that of a noble gas. And transition in heavy metals that have pseudocore D sublevel electrons can also lose these D electrons, giving them the ability to form multiple ions with different charges.